This video is about free body diagrams, what you should include and how you should draw them. In this course, again, you're expected to show your work. In your show work, you're to include the problem number, name, and date for each problem. This is to keep track of things and have you know who and when the problem was solved. A clear problem statement. What are you going to find? This is important. If you don't know where you're going, sure enough, you'll get there. Given information. Essentially gather the information. Read the description and problem description and again, gather the information. An important part of the problem solving process is the free body diagram. This is where you organize the information. Statics is a very visual course, so making a drawing is a good way to organize the information. Define all variables. Just sticking a variable in an equation isn't very good when you go to look at the problem. Maybe you'll want to look over this problem in a few weeks when you're working an exam. You need to know what you did. And if you don't know what the variables are, how can you do that? All solution steps. Again, the steps should be clearly shown what you did. And when you do your steps, identify what the step is. It can be as simple as sum of the forces in the x direction equals 0. But that should be on there. Just writing an equation, I don't know what it is. When you get your job, people will be reviewing your work all the time. And you need to know what you did, what properties you applied. Your final answer should be highlighted, box or underline. Make sure you include units and direction as appropriate. This really is the engineering problem solving process. We look at what we're after, what's the question, gather our information, try to organize the information in a drawing, and then go to solving the problem. And when we solve the problem, again, we need to know what we did, what relations or equations we applied. So here we have a problem. It's a picture. What are you to find? What is your goal? That's the key questions you have to ask yourself when you have this type picture. So once you know your goal, you can look at what's your boundaries. What are you going to include? What's inside your problem or part of your problem, and what's not part of your problem. You could include everything that's shown here above the ground, which would be good if you were looking for the reaction forces at the bottom of this wall or pole or whatever it is. We could just include the weight, or this object here. Notice the weight of the object is an external force, even though it's inside our drawing. The force comes from outside of the drawing. We could just include part of the rod or beam or whatever it is here. This would be especially appropriate if we were looking for internal forces at that midpoint. Or we could include the whole rod or beam and how it's, which would be good if we're looking for the forces at the wall where it's connected. So, what are your point area volume identifiers? Many of these are given to you in the problems that we have, But if you're working a real problem, you'll need to identify them. And we usually identify them with capital letters. A, B, and C are the points of interest. And we need to know what our variable names are. So you could define it later. Say LAB is the length from A to B. Fairly simple. You don't need to be real elaborate on your definitions, but you do need to include your definitions. You could also include it on the drawing. You could just write LAB along this direction somewhere, and that would define the length from A to B because it would be obvious that that's what it was. What are the forces on our object that we have identified here as being included? Well, we have a downward force here from the weight, and we'll call that W. And we have a tension in the cable going up. We'll call that TAB, because it's a tension in the cable from A to B. Again, including it on the drawing, it's obvious what it is, and you don't need further definitions. We're after the reaction forces, so we'll label these reaction forces R at C in the Y direction and R at C in the X direction. An important thing to include on the free body diagrams is, of course, your reference, what's X and what's Y. So you should have, again, your directions identified in the free body diagram. So what are couples and moments? We'll cover those in Module 2, but think of it as, you may have heard it as a torque, same thing. And again, we have to give it a name, MC, moment at C, which is good for 2 dimensions. So we could have an angle reference. You could draw theta B as shown. You may have wanted your angle to be relative to the vertical rather than the horizontal. So you would have drawn your angle here. Again, it's your definition. You define which way these forces are going, left or right, and you define the angle. You could have defined an angle up here. So here's an example problem. We're only given words, we're not given the drawing here. So what is a child's pushing force? Well, we define our directions first. So we're on a 10-degree ramp. Again, we're taking the information given and organizing it into a drawing. We have the force of the child, which is what we're after. So we need to have that on our drawing. We also know this wagon has a weight, so we put the weight of the wagon pointing downward. We also know the ramp is going to push up on the wagon, so we have a normal force, Fn, and we have a friction force. Now the wagon doesn't need to be anything special. Again, keep it simple, enough to recognize what things are, but you don't need to repeat the drawing given with the problem. And again, we're given information. We're given the force coefficient of friction, so we know that the friction force is equal to 0.21 times the normal force. We don't know the direction of the friction force, but we'll find that out later. We've assumed a direction. Again, it's important. The direction you assumed is on the drawing. And we'll find that maybe the original coordinate system we used wasn't the best for solving this problem. This problem's actually better if we rotate the coordinate system a little bit to make the problem a little easier. So here's another example problem similar to our drawing. And the question is, find the tension in the cable attached to the wall. Well, we know the tension in the cable around the frictionless pulley stays the same. So our free body diagram could just include whatever this weight is that we have hanging there. And again, we draw the forces on it. We have the force due to the weight. We might call it W, call it FW. Again, what you call it isn't important, but it needs to be defined. And it could be defined on the drawing. Again, T is the tension in the rope. But if we have a different question, same drawing, different question, but now we're looking for the reaction forces at the wall. We could just include the rod or beam or whatever it is here, but we want the forces at the wall, so it's probably best to include the attachment point up at the top. So we define our coordinate system. And again, our drawing doesn't need to be much. A simple line is sufficient for the beam and the cable. And we add our point names and our distance names. If we were given C was 3 feet, you could put 3 feet there. You don't need to use C, but you can put values. So our forces that we have the weight and we have TBC. We know they're the same magnitude because they're going over the pulley. And we have our prior free body diagram, which allowed us to find the weight and the tension. We have our reaction forces. And we have a reaction moment. Moment at A, I drew it as positive. You could draw it negative, but when you go to your answer, you'll have to include which direction it turns out to be. We could have an angle, or optionally, we could just have the length and not have the angle. The reason for that is, of course, once we decompose TBC into X components by adding our X subscript, or we could have drawn it originally, reaction at C in the X direction, or define reaction at C in the X direction. And we know it's the tension in BC times tangent of theta if we use theta, and we know it's the tension in BC times C divided by LBC if we used the length. I find using the length is easier, but a lot of people like to use the angle. Let's say we've got a three-dimensional problem. A lot of people have trouble with their free body diagrams on three-dimensional problems. Say we're given the wing, and we have dimensions to the effective attachment point and wing center and engine center as given here. So do we need to draw this in 3D? Well, we could draw it in 3D, but we don't need to draw the wing. We can just draw a line. Say that's the wing. We have our points identified. I put B at the end of the wing. E is the wing center. D is the engine center, and so on. Now putting distances and forces on this drawing can get quite complicated. So let's put the forces on. we have the wing forces and the engine forces. And again, we're supposed to find the reaction forces. So we put reaction forces in the X, Y, and Z directions. And we also want to put moments. Now in 3D, it's kind of hard to draw the little arcs. So a lot of times we use a double-headed arrow to represent a moment. Again, that's the way your thumb would point, your right-hand thumb, for the moment, so we can keep things straight. Notice I drew MZ in the negative Z direction and RZ in the negative Z direction. That's fine. That's the direction we assumed, and we'll use that in solving the problem. But when you do the direction at the end, if RZ is negative, you'll say it's pointed in the positive Z direction instead. But a handy thing to do is to draw a two-dimensional problem. Here we're just looking down the Z-axis, so we put Z coming straight out at us. And we have X and Y. We put our distances on, and then we add our applied forces and reaction forces. Here we haven't included anything in the Z direction. And here's the moment. Again, it's a negative moment as we drew it, so we assume a negative direction, which is clockwise. When you do 2D drawings, you should do the drawings, have at least 2D drawings usually. Not always, but 2 drawings are useful. And all the action occurs up here. And again, so that would be pretty small. So don't make your drawings too small. A lot of people make them too small. So let's make it a little bit bigger. Same thing, just bigger. And we can include our distances on here. And our thrust and our drag. Being consistent with the 2D drawing. For our names, we want to name them the same. Our reaction forces in X and Z. We have our moment. Only one moment shown here. We could again use double arrows for the other. Now what if we have a force pointed down? So it's down in this view. A downward force can be represented with a circle with an X in it. So think of an arrow going down, and an upward force is a circle with a dot in it. But we have 2 forces at this location, so we have L and W at the same point. Free body diagrams, again, are a critical part of defining and solving statics problems. They're also critical parts for dynamics, fluids, materials, and most all engineering problems. You need the drawing to organize your thoughts.